All right, so we're going to start talking about chemical reaction stoichiometry. So what we're going to start to do is weave the chemistry concepts that you've learned in all of your previous classes into how we actually do mass and energy balances. So as our little refresher, if we have a reaction where A goes to B, so A being reactants, B being products, we can impose constraints on the relative amount of the reactants or products that are formed as a result of what we do to the input and output streams in a mass balance. So if, for example, you start with 1 pure mole of A, you will not necessarily get 2 pure moles of B in reality, right? So it would be 1 to 1 if it was perfect stoichiometry and the reactor functioned perfectly, but that's not real life. So basically what's going to start to happen is we're now not able to reduce our general balance equation to input equals output. If we said that input equals output, we are assuming 1 pure mole of A becomes 1 pure mole of B if we have a reaction occurring, right? That's basically what's happening. So now we have generation and consumption occurring because we're consuming products and we're consuming reactants and we're generating products. So that's going to now be very important to us. So when we have a statement of the relative number of molecules in the reactants and the relative number of products that are participating in a chemical reaction, we call that a stoichiometric equation. So for example, let's say that we have 2 SO2 plus 2 O2 generating 2 SO3. That is a stoichiometrically valid equation. A valid equation must be balanced, and that means that we have to have the same number of atoms on each side of the equation. So we have 2 atoms of sulfur and 2 atoms of sulfur on both sides of the equation, and we have the same amount of oxygens on both sides of the equation for that example. So remember, the reason that this is because you can't create or destroy atoms in chemical reactions. If you're creating or destroying atoms, we're in big trouble, right? So just the same as mass, we can't create or destroy as we go forward. So one thing that's going to be important to us is what we call a stoichiometric ratio. And it's a ratio of 2 different molecular species. And it's basically the ratio of the coefficients from the balanced equation. So we always have to balance the equation first in order to get a stoichiometric ratio. So for example, if we go back to that same equation where we have sulfur dioxide and we add oxygen and we get sulfur trioxide, 2 moles of SO2 reacted per every 2 moles of SO3 produced is a stoichiometric ratio, the one that's on the left. We can also write that 2 moles of SO2 is consumed for every 2 moles of SO3 that is generated. So the numbers are coming from the balanced equation. When anything reacts, it's consumed. When anything is produced, that is related to generation. And that's going to be really, really key. So circle that, highlight that, whatever you need to do in your notes. Reactants are related to consumption, and products are related to generation. That is a key thing that you need to know going forward. All right, so the ratio is the number of reacted to produce, consumed to generated, things like that going forward. So now if we apply this to mass balances, well, let's say that we have 1,600 kilograms per hour of SO3 produced, and we want to know how much of O2 is consumed. So the same chemical reaction that was on the previous slide. So one of the things here that we have to do is we have to use that stoichiometric ratio, but that stoichiometric ratio is in moles. So I'm going to grab my laser pointer here. If we start out with something in terms of kilograms per hour, we're going to need the molecular weight first, right? We've got to get it back into moles, right? So we're going to take kilograms per hour and we're going to convert to kilomoles per hour, basically using the molecular weight. And then the stoichiometric ratio is the key thing to everything going forward when we do these types of mass balance problems. 1 kilomole of oxygen is consumed for every 2 kilomoles of SO3 that's produced. So what that's done is it's moved us from SO3 to O2. Then we need to go back and we need to say, well, what is the molecular weight of O2 and the molecule, not just oxygen itself, right? Oxygen itself is 16 grams per mole. But that means that O2 is 32 grams per mole, or remember, it could be 32 kilograms per kilomole. And that's going to tell us that we have 320 kilograms per hour of O2 produced. So this right here, this concept that we just talked through, this is key to everything that we do from now on in this class. if we have some kind of a rate of one substance and we want to know the rate of the other, we must go through the stoichiometric ratio, and that's really critical. Okay, we must be in moles if we're going to relate products and reactants. And it's also really good practice to say generated or consumed or produced or whatever when you're writing these moles, because it will remind you of what goes where. So it's just good practice. It's not something I require in this class, but it's something that might be good to get in the practice of if you struggle with some of these types of concepts. The last thing that I want you to do is I want you to consider the following reaction that's on the screen, and I want you to pause the video and try to answer these questions. All right, hopefully you paused the video. The first question that we always have to ask ourselves is the stoichiometric equation balanced? Well, in this case, yes, it is. There's the same number of atoms on each side. We have the right coefficients where they need to be. The second question we want to ask is, what's the stoichiometric coefficient of CO2? Oh, that's just simply the number that's in front of CO2, and that's a 4. The last question is, what's the stoichiometric ratio of H2O to CO2? And this is the important question for 210, right? It's going to be 4 moles of CO2 are generated for every 4 moles of H2O that are generated. And so there's actually a ratio between things wherever they are on these sides of the equation, right? So we can have 2 products have a ratio of each other, or 2 reactants have a ratio to each other. That's why the generated and consumed is so critical in this particular example and when we do stoichiometric ratios. So hopefully that's a lot of review from chemistry. If it isn't, go back through and double check that you really understand this last concept, this stoichiometric ratio. That is going to be the key concept going forward in this class.